All right, so today we're going to look at forces with rotation. When you have forces with rotation, you of course also have torques. You pretty much need both to solve any problem that involves forces. Okay, let's get into it. So the classic is trying to find like tension in a pulley. That's a really classic force problem. So let's go ahead and set that up. Okay, here is a classic example where you have two different masses, M1, M2, on a surface. This can be frictionless, but you have a pulley that has a mass, MP, M pulley, and it has a non-negligible radius, R. So its moment of inertia matters. Okay, so here we can start by drawing a free body diagram. So let's take M1, and we will have a tension on M1. There are no other forces on M1. Let's take our pulley. Let's draw our forces on our pulley. We're going to have this tension, T1, and we're going to have a vertical tension. They will not be the same. And then on block 2, we'll have a vertical tension. So I'd like you to predict which one will be greater, T1 or T2. Okay, so you should predict that T2 will be greater than T1 because T2 has to accelerate the pulley and pull M1, while T1 really only has to accelerate that first mass. So you can begin with Newton's law, translational form. And so let's take the bottom pulley and, oh shoot, we forgot gravity. Just kind of a big deal. No gravity, no fun. So when we sum forces, let's make the downward direction the direction of acceleration, positive. So we'll have this expression for M2. Now we can go ahead and we can do that again for M1. There's only T1 that pulls M1, so the expression is much shorter. Now we could set up forces again for the pulley, but on the pulley, the acceleration linearly is 0. So we won't set up forces for the pulley. We'll set up torques for the pulley because the pulley is rotating with an angular acceleration. So as we fill in torques on the pulley, let's look at our pulley. At a distance r away, we have T1. At a distance r away, we have T2. So as we fill in our torque terms here, you're going to have two terms. You're going to have torque from tension 2, so we'll write it like this, T2, distance r, and we'll subtract off the distance r times T1. Remember that torque is r cross F. And here we'll just define the positive direction as the direction the system is moving. That will be okay. Now, when we set up our I, we can write it as 1/2 mass of the pulley and radius squared. This is because the I of a disk is 1/2 mr squared. Now, you can rewrite alpha so that you can connect it with these other A's. So alpha is the angular acceleration of the pulley. And we can connect it to the acceleration on the edge of the pulley using A equals alpha r. So instead of writing alpha next, what we can do is we can write it as A over r. And yes, this r and the other r's are all the same r because they are all radius of the pulley. The string is connected on the outer radius. This allows us to cancel some r's, then cancel some r's because of the other side. And we end up with an expression that says T2 minus T1 equals 1/2 mass of the pulley times acceleration. And you'll notice that almost looks like a force expression, right? So now we have three equations, 1, 2, 3. Units make sense for both. So we can go ahead and solve this any way we like to find A. My suggestion is to solve for T1, T2, and sub it in. So we'll put in T1, and then we can go ahead and we can sub in T2. Then what we can do is we can get all our accelerations to the same side. So we'll have m2g equals
for A.
out front. And then to get A by itself, we can divide.
There we go.
Check that your units make sense. The mass units will cancel out and you'll be left with units of acceleration that are gravity units. That does make sense. The next thing we can do is we can go back and we can plug acceleration into any of our tensions. So for example, if you wanted T1,
Just go ahead and
say, well, from above, T1 equals M1A. So you go ahead and just put this A right there. Bam. And you can do that same thing for T2. Okay, let's apply our force and torques technique to another classic, ball rolling down incline. We can make our incline an angle theta. All right, this ramp needs to have a friction force. There needs to be a mu, because if there's not friction force, there's no way to have perfect rolling. So let's go ahead and draw our forces on our ball. Okay, here's our ball. Here's a little bit of the surface right here. We'll have a normal force that's perpendicular to the surface. We will have a mg from the center of mass straight down. We'll have a friction force pulling up. Okay, now what is the rotation point? The rotation point is the center of our object. So if we begin to write out, let's say, the torques, there's only one of these forces that will create a torque. So if you look, the only reason why this object rolls, which is what I was saying you need to have friction, is friction. Mg is applied directly at the pivot point. So there is no R value. Remember, each torque is R cross F. So you're summing these up. And for us, there are three of them. 1, 2, 3. And Mg, we get an R of 0. So if this is the force of gravity, there's no R. Okay, then when we go ahead and try it for the normal force, you get the normal force runs straight through the center. So there's no cross product. That makes this term go away. Okay, let's try it for the friction force. So the friction force does have this radius value cross product. So the only torque that we're going to have is the torque due to frictional force. You can plug in our I value. You can plug it in as some sort of X factor. Now what I mean by that is for a hoop, you would say 1 mr squared. 1 would be your X factor. For a disc, you would say half mr squared, and half would be your X factor. For a solid sphere, you would say 2/5 is your X value. So this way we can find any shape we want later. Okay, so then we'll have alpha. All right, nice. That's the rotation part of this. Then go ahead and still apply all of your force expressions so you can sum the forces in the X. Ooh, wait a minute. X. Let's kind of tilt our coordinate system. So let's work in a coordinate system that goes parallel and perpendicular to the ramp like this. So if we do that, we'll need to break up mg into components like this, with this being the angle theta. So we'll have mg sine theta, and we'll have mg cos theta. Okay, cool. Now I'm ready to go. So let's sum the forces that are maybe parallel to the ramp and set them equal to ma. So the forces that are parallel to the ramp, mg sine theta is pulling down the ramp. Friction force is pulling against it. Great. Let's connect these two expressions together, because alpha and A, if there's perfect rolling, they'll convert directly into each other. A is talking about the center of mass acceleration, while alpha talks about the angular acceleration of the disk. And if the disk is perfectly rolling down, then they'll just be connected through R. A equals alpha times R. So above in this expression, let's take our alpha value and let's replace it with A over R. This allows for a good amount of simplification here. Our R can cancel. Bam. And, oh, wow, our R can cancel again. So now we have an expression for friction force. Do you see it? FF equals XMA. So let's go ahead and take the expression up above, this FF equals XMA. and plug it in down here. So we're going to plug in. Okay. Now let's just go ahead and get a's all on one side, and then we'll be able to solve. So that will look like this. We can pull a out, and we find acceleration is, whoa, and then the m's cancel. Nice. So this lets us find the acceleration using forces on a ramp. If you want, we can find the necessary mu needed for perfect rolling. Just take it one step further. So let's go ahead and find some mu. So if you want to find mu, let's write our next expression for force. And when you set this up, the acceleration perpendicular to the ramp is 0. Versus Fn will equal mg cos theta. Cool. So now connected with mu. You want mu? What is mu? Mu is ff over fn. Well, you just found fn. Fn is mg cos theta. And from this purple expression above, you found ff. Ff is xma. So over here, you'll put x. That's just a number, remember, depending on the shape. 1/2, 2/5, etc. So x times m times a. G sine theta over 1 plus x. And then it simplifies beautifully. The m's will cancel. The g's will cancel. You'll have x over 1 plus x. Then you'll have sine theta over cosine theta, also known as a lovely sun-kissed English gentleman. Tangent theta. That's neat. So our mu is x over 1 plus x tan theta. If our mu is not large enough, you cannot have perfect rolling, and you can't make the substitution we made in red, a equals alpha r, which got us all rolling.